Hello and welcome to the next part of this series. Until now, we have done two types of analog to digital converters, simple counter type and tracker or continuous type analog to digital converters. There is also a short revision video for these converters. Please see to it for a brief overview. In this video, we will talk about flash type analog to digital converters, also known as simultaneous ADCs. Let's start with the construction of a 2-bit ADC. So you must be thinking, why 2-bit? In the previous videos we saw all the converters in 4 bits. You will come to know why once we finish its construction. In the converters we saw earlier, we had counters. If you know about the work of counters, then you would definitely know that they are a part of a sequential circuits and hence depend on the previous outputs. But there is a different story with flash type analog to digital converters. They don't have counters, nor do they have digital to analog converters. A flash type analog to digital converter can be easily constructed with some resistors, op-amps and priority encoder. For those who don't know priority encoders, let's take a brief look at its working. A priority encoder, as the name suggests, gives priority to something, and here this something is the most significant bit. In the binary coded system, the most significant bit or MSB is the first bit you see as you read the binary code from left to right. Say for a code 1011, a 4-bit binary, 1 at position I3 is the MSB. A priority encoder looks for 1 as an input signal and converts the input suffix to its respective binary code. And as it gives priority to MSB, it first checks for the MSB to be 1. If not so, it moves to the next bit with the lesser priority. For example, if we have number 1100, the input I3 and I2 have 1 as input, but giving priority to MSB, that is I3, it gives the output 11, which is binary equivalent of 3. If the input say is 0101, its output is binary equivalent of 2, that is 10. We will further see it in action when we will discuss the working of flash type analog to digital converters. For now, let's start with its construction. For the construction of the flash type ADC, let's start by selecting the priority encoder. Since we want 2-bit output, we will require 4 bits as input. Why so? This is because encoders follow 2 to the power n input is to n output ratio, where n is number of bits for output. Each input of the priority encoder is connected to an op-amp except the last, which has the binary 1 input by default. Last input or LSB is kept 1 as a priority encoder can only work when one of its input is 1. And LSB having lowest priority does not interfere with its working. The op-amps here are connected as comparator and as usual will perform comparisons between input and a reference signal. In this ADC, reference signal is constant and does not change with output as in previous two analog to digital converters. This non-changing reference signal is given to op-amps inverting terminal through a series of equivalent resistors which divide the reference voltage in smaller parts as we go down. The input signal is fed to the non-inverting terminals of the op-amp directly. As it can be seen, for a 2-bit output, we have 3 op-amps and 4 resistors. Similarly, for a 3-bit analog to digital converter, we have 7 op-amps and 8 resistors. For a 4-bit analog to digital converter, we would have 15 op-amps and 16 resistors. And the number seems to grow rapidly with each increase in the bit, with the relation as 2 to the power n minus 1 op-amps and 2 to the power n resistors, where n is the number of bits in output. So, with more bits, the analog to digital converter becomes big, costly, and bulky. And with lesser bits, we have a lesser resolution and precision, and this is its major drawback. In the previous videos, you may have often caught me saying flash type analog to digital converters are fastest. Let's see how. As we see, it's working. So, as I said, all the resistors in series are equal. After applying voltage division law for series connected resistors, we have the following reference voltages for op-amps. Starting from the bottom, op-amp 1 has a reference voltage V by 4, op-amp 2 as 2V by 4, op-amp 3 as 3V by 4. Here V denotes the reference voltage. Now let's assume input voltage is somewhere between 3V by 4 and V. Then it is greater than all the applied reference voltages. Op-amp 1, 2 and 3 all have 1 as their output. Priority encoder gives priority to op-amp 3 output, our MSB, and will have the output 1, 1. If input voltage ranges from 2V by 4 to 3V by 4, op-amp 3 has 0 output. Others will have 1. Now, priority encoder gives priority to op-amp 2 output, and the priority encoder will give its output as 1, 0. Similarly, if input voltage is between V by 4 and 2V by 4, priority is given to the output of op-amp 1, and the encoder gives output 0, 1. When the input goes more or less, say lesser than V by 4, no op-amp gives the output 1, but we have LSB equal to 1, and hence the output is 0, 0. As you can see, the encoder generates an output as the input changes, and hence is termed as the fastest. Due to their fast conversion speed, these converters are often used in systems where speed matters and not the cost. For example, digital oscilloscopes. So this is all for now. Next we will see dual slope analog to digital converters. If you find that I missed something, let others know and don't keep it to yourself. And if you liked it, do like and subscribe. Simple way of learning. Thank you.